So let's take a look at the vapor compression cycle again. We have learned this in topic 1.1. If you look over here, okay, at the left hand side, okay, so let's say the compressor inlet, we call it 0.1, okay, followed by the compressor outlet 0.2, okay, and the condenser outlet 0.3, and the evaporator inlet 0.4. How do we represent these 4 points in the pH diagram? So remember, for compression to take place, your refrigerant must exist as gas. Okay, because you cannot compress a liquid. You can only compress vapor. So if you can only compress vapor, that means 0.1 and 0.2 should be at the right hand side of the pH diagram. Okay, at the vapor state of the pH diagram. So initially, let's say it's over here at around 380 kilopascal, okay, and a temperature of maybe around 30 degrees Celsius or 35 degrees Celsius, and it undergoes compression. So what is the most obvious change in properties when the gas undergo compression? That will be the pressure, correct? So if the pressure start to increase, your arrow, okay, your line will start to move upwards. Okay, it will start to move upwards. And note that it is moved slanted. Okay, it is moved in a diagonal direction, because this line, right, it can never cross the very thin blue line that you see over here. Okay, you notice there's a thin blue line, and it's called entropy. I'm not going to touch this term entropy because it's actually very it's not a very simple term to understand, but you need to know that for compression process, it's bounded by this entropy line. If it's steeper than the entropy line, okay, that means your process is more than 100% efficient, which is impossible. There's no such process. So no matter what, it must be either on the same gradient as the constant entropy line, or it must be more gentle than the constant entropy line. Okay, so let's continue from point 2. From point 2 to point 3, right, we know that your refrigerant actually start to lose energy because heat rejection is taking place at the condenser side. So your refrigerant lose energy, so it will start to move towards the left. It will move towards the left hand side, because when it moves towards the left hand side, enthalpy value will start to drop if you look at the x-axis of your diagram. So when it's moving left, enthalpy starts to drop, okay, and you will be cooled down, your refrigerant will be cooled down, and at this point, okay, at the saturated vapor line, what happened? Okay, your refrigerant actually starts to condense. Okay, so the vapor will slowly be converted to liquid. Okay, from 100% vapor to 90% to 80%, and all the way until it's at the saturated liquid line. That is where your 100% of the gas become liquid. But of course, if let's say you continue to cool down some more, then your temperature will start to drop. So the final temperature maybe is around 40 degrees Celsius. Okay, so what's next? From point 3 to point 4, remember in topic 1.1 we mentioned, it will cause a sudden decrease in pressure, a sudden drop in pressure through this expansion valve. So when there's a drop in pressure, of course, it will move down the y-axis. So from maybe around 1.5 megapascal, it starts to drop all the way to 380 kilopascal again. And this time around, it can move in a vertical line. Okay, to make things simpler, it's always moving down in a vertical line. Enthalpy, no change, just simply a change in pressure. And finally, at point 4, we know that from point 4 to point 1, your refrigerant gains heat. Your refrigerant is absorbing heat from the surrounding hot air, surrounding warm air. So what happened to the enthalpy? It will start to increase. Okay, it will start to increase. So it will start to move towards the right hand side. The arrow will be pointing towards the right. So this cycle, okay, will be represented in this pH diagram, and the shape of the pH diagram will always look something like this. It is like a trapezium, okay, where the top line is longer, bottom line is shorter, and there's a slanted line at the right hand side. So the whole process that I've just explained can be found in this slide. Okay, for process 1 to 2, 2 to 3, 3 to 4, 4 to 1, and what's actually happening. Okay. So let's put some numbers into what I've just discussed with you. So you will notice that there are some terms over here such as PE, TE, PC, TC, T1, T2, T3. So what are all these terms represent? Okay, what are they representing? So first, you may want to write it down, okay, above the diagram, above the vapor compression diagram at the left hand side. So T1, okay, is actually the temperature, okay, temperature at point 1. And what is point 1? Point 1 is your compressor inlet, So to describe this temperature in words, it will be the compressor inlet temperature. So T1 is your compressor inlet temperature, and for this particular diagram, it is 37 degrees Celsius. So after going through compression, okay, it will go to point number 2. So point number 2, if you want to talk about the temperature at point number 2, it is actually your compressor outlet temperature. Compressor outlet temperature. So how about T3? T3 will be after passing through the condenser. So T3, you can call it the condenser outlet temperature. And finally, you have T4, which we don't really use it, we don't really give it a name, but of course you can call it the evaporator inlet temperature. So just try to remember these 3 temperature names, okay, compressor inlet, compressor outlet, and condenser outlet. How about TE? You notice there's a TE and TC. So TE is at the bottom line, TC is at the top line. So same thing, T represents temperature, and this TE is actually your evaporating temperature. Evaporating temperature, and TC will be your condensing temperature. So as for PE and PC, it's the same thing. PE is evaporating pressure, and PC will be condensing pressure. So these are the few terms that you have to know, okay, you need to know, so that when the question actually asks you, give you some information in words, you know what it actually represents. Okay? So let's try one example question. So given that the conditions below, draw the cycle on the pH diagram. So how do we approach this question? If you want to try, you may pause the video and try out the question yourself on this slide. If not, I will continue. Okay, I will go through the question on how to do this question. Okay, you are given 5 information. Okay, so you are given the evaporating pressure at 0.45 megapascal. Okay, you are given the condensing pressure 1.4 megapascal. Okay, and the 3 temperature, compressor inlet, which is your T1. Okay, compressor outlet, which is your T2. Condenser outlet temperature, which is your T3. So how are we going to use these 5 information, which is enough, okay, to draw out the trapezium shape thing? So first, you will always try to draw the 2 lines first, the 2 horizontal lines. That means the condensing pressure line and the evaporating pressure line. These 2 information is very crucial. So first, we know that the evaporating pressure is at 0.45 MPa. So you try to go to the y-axis of your diagram and look for 0.45 MPa. You cannot find because it's in terms of kilopascal over here. So 0.45 MPa is in fact 450 kilopascal. So this line is 200 kilopascal. The next dotted line is 300, followed by 400, and finally you have a 450 pascal. So your bottom line will be along this 450 kilopascal line. So you may want to just draw a line first to represent this PE. Okay, PE, which is equal to 450 kPa. Okay, 450 kPa. And similarly, go and draw the condensing pressure line, which is 1.4 MPa. So same thing, you have 1 megapascal over here. The next line is 2 megapascal. So you will have to do your own estimation. So it's slightly below, slightly less than half. Okay, and draw a line all the way. Okay, so this one will be your condensing pressure, which is 1.4 MPa. Okay, so next you need to find a specific point at this field, this 1, 2, 3, and 4, okay, such that you can complete the whole diagram. So that is when you need to use the 3 temperature that is given to you. First, let's start to plot point 1. Point 1 is compressor inlet, and it has a temperature of 40 degrees Celsius. So over here, okay, 40 degrees Celsius is here. So you know that point 1 is always at the bottom line, okay, at the evaporating pressure line. So you have to follow this 40 degrees Celsius constant temperature line. So 40, 40, 40, okay, and continue to move down, 40, 40, 40, until it's at this particular point. This is your evaporating pressure at 450 kilopascal and temperature at 40 degrees Celsius, which is the point 1 that you want. So just put a cross and label it 1. Using the same idea, okay, try to find point 2. Point 2 is actually 80 degrees Celsius because compressor temperature, outlet temperature is 80 degrees Celsius, and it will hit the top line. So 80 degrees Celsius hitting the top line is somewhere around here. Okay, so this is your point number 2. Because 80 degrees Celsius line, you continue to move downwards, it is actually over here. How about point 3? Point 3 is your condenser outlet. So you know that it should be at the left hand side of point 2. So 40 degrees Celsius is over here. So you continue moving up, it will be this point, point number 3. That's it. Okay, that's all the information you have, and you have already used all the information. Then you may ask yourself, what about point 4? You don't have any information about point 4. So what can you do? Okay, remember that from 3 to 4, right, is always just a vertical line downwards. Okay, it's always just a vertical line downwards. So if you draw a vertical line and you hit the bottom evaporating pressure line, that is your point 4. So with that, complete your diagram by joining up 1, 2, 3, and 4. Okay, so this is your completed diagram. I will try to bold it. Okay. So this is your completed pH diagram. Okay, so please draw this diagram onto your own notes. Okay. But of course, you must know how I arrive at these 4 different points. Okay, so let me repeat. First, you draw the evaporating pressure line and the condensing pressure line. Next, using the temperature given, okay, plot point 1, point 2, and point 3. And of course, point 4 is just vertically downwards. Then lastly, the third step is to join up these 4 points. So that will be your completed pH diagram. Okay, so you may want to pause the video and try to finish up your diagram first before you proceed. Okay, with the diagram you have just drawn, fill up the following information, because there are some other extra information that you can get from this particular pH diagram. Okay, so first they ask for TC. What is TC? So just now I actually mentioned TC is your condensing temperature. Condensing temperature is actually a temperature over here. So TC is the temperature at this horizontal line. You will notice that it's in between 40 degrees Celsius and 60 degrees Celsius. So it's maybe around 50 or 51 or 52. So don't worry that your answer is slightly different from mine, because there's always some degree of error when you read off from the chart. So in this case, it should be around 50 to 52 degrees Celsius. Okay, so maybe I'll put 51 degrees Celsius. How about TE? Okay, so TE is the evaporating temperature, which is at this horizontal line. It's between 0 to 20, somewhere above half, okay, of this gap. So maybe around 12 degrees Celsius. And lastly, they also ask for the enthalpy value. Okay, so how do you read off enthalpy value? You will have to draw a vertical line downwards, okay, until it hit the x-axis. So first point, okay, is your H1. That means enthalpy at point 1 is between 250 to 300. So it's maybe around 280. Okay, 280 kilojoules per kg. So similarly for point 2, if you draw a line downwards, it's around maybe 310. And finally, H3 and H4 is the same. Okay, they have the same value. It's slightly more than 100. Maybe it's around 100 and 105 or 110. So with that, please fill in all this. Okay, fill in all this information. So H1, okay, it can be 280, or if you write 275 or 270 is correct as well. Because as I mentioned, there will be some degree of error. So here maybe 310 or 305, and this point is maybe 105 or 110. Okay. So lastly, okay, the next example we have, how do we determine these two pressure? How do we know it should be at around 400 kilopascal or 450 kilopascal or 350 kilopascal? So how do we determine this pair of pressure or this pair of temperature? So take note that, for example, if I want to cool down a room, okay, a room that is 24 degrees Celsius, I must supply air at maybe around 17 or 18 degrees Celsius in order for my room to become 24 degrees Celsius. Okay, so a common misunderstanding is when you change your set point, okay, at your remote control, when you change the set point to 24 to 23, it is not changing the set point of the supply air. It's not changing the set point of the air that is coming out. It is changing the set point of the air that is returning to your air conditioning system. So in order to have a low temperature room, your supply air has to be even lower. So maybe at 16 degrees Celsius. So in order to get air at 16 degrees Celsius, what should the temperature of your refrigerant be? It has to be even lower. Your refrigerant temperature may need to be at around 12 degrees Celsius, such that it can bring your temperature from 24 degrees Celsius all the way to 17 degrees Celsius. Okay? So in order for heat to be removed from a cool space, your evaporating temperature must be lower than the cool space or the supply air temperature. So there must be a substantial delta T. Okay, this temperature cannot be too high. If your evaporating temperature is around 20 degrees Celsius, there's no way that it can produce air at 20 degrees Celsius. Okay, or 19 degrees Celsius. It will be higher. Definitely, it will always be higher. Okay, and the best it can get is to be equal to your evaporating temperature. So with that, okay, once you have determined the temperature, it will have a certain pressure. Okay, and because of that, your condensing pressure, same thing. Okay, it depends on how well you actually remove heat from the condenser, and you will have a certain pressure. Okay, so that is the reason behind. So we will stop over here, okay, before we continue with the next part of the lecture.